Okay, so we are going to look at a natural logarithm today and a base of e. So we get a new number here. If you look at your calculator and you look down to where the logarithm is, just to the left you'll see something called e to the x, and if we click on it, it gives us e to a power. So if I do e to the first power, it gives me a number about 2.7. All right, and this number is going to be really important in application problems. We see it throughout the rest of our high school math classes. So just like pi is about 3.14, right? And it's an irrational number, so the decimal goes on, never stopping. Same with square root of 2. We have this new number called e, and that's approximately 2.718. We call this the natural base function. Now, when we write the natural logarithm, just like when we had the common log where we didn't have to put anything in our base, we assume that that has a base of 10. So with natural logarithms, we use, instead of log, we use ln, and that represents a log with a base of e. So really, there's like a little invisible e as our base. Now remember, e is a number. E is about 2.7. Here are a few properties of natural logarithms. E to the natural log of x gives us x. Natural log of e to the x gives us x. The reason, remember with the power rule, we can move the x to the front, right? So natural log of e. Well, what's natural log of e? It's 1, because remember, what this means is log base e of e. Right? So we're going to write that that is equal to 1. Okay, here we go. We want to write each exponential function in logarithmic form. Okay, so let's think about this. This becomes log base e of 23 equals x. Okay, now I don't want to leave it like that. I want to rewrite this as natural log of 23 equals x. So that log base e, I just want to rewrite that as with the letters L and N. Okay, let's see this one. So log base e of x is going to give us 4. So again, I just want to make sure log base e is rewritten as natural log ln of x equals 4. Again, this just goes back to how we write something from exponential form to logarithmic. Now we want to go backwards. So we're going to take each logarithmic equation, and now we want to write it in exponential form. Now again, remember, natural log of x is really just log base e of x. So now when I rewrite it, I'm going to have e to the power 1.2528 equals x. And that's it. Okay, so I'm just rewriting it as an exponential function. Natural log of 25 equals x. So again, remember there's a little invisible e as my base. So little base becomes big base. Exponent goes there, equals 25. Okay, we want to condense these to write it as a single logarithm. Now remember, natural log, we treat the same, right? Same properties as logarithms. Okay, so for example, I see I have a coefficient of 3 here and a coefficient of 2. So remember, we can move that coefficient so that we have a power, we have an exponent. So that's going to be natural log of 1/2 to the 3rd power plus natural log of 6 squared. Next, remember when we have addition of logarithms, that can be changed to multiplication. So we'll have natural log of 1/2 to the 3rd times 6 squared. Now I have it expressed as a single logarithm, but of course we don't want to leave it like that. So let's go ahead and multiply. So 1/2 to the third power is 1/8. 1/8 times 36. And then can that be reduced? Yeah, that's just going to be natural log of 9/2. And then we just leave it like that. Okay, same thing. Now, here I have a minus. Now, one way I can think of subtraction sign is I can think of this as, that's our division, but I have two minus signs in a row. Before we do that, though, let me just move the 2 to the exponent. So it'll be natural log of 3 squared minus, now, if I factor out a negative, this is kind of an optional step, and I'll just kind of show you how that works. Because I'm really going to turn this into subtracting these two. So that's really, let's see, 3 squared is 9, minus, so what's the plus turn into? It turns it into multiplication, right? So I'm going to end up with 4y. And now I'm going to turn the subtraction natural log of 9 over 4y. Now, I don't necessarily have to factor out the negative. What you can just remember is anytime there's a negative sign in front, just remember that you're going to put that in the denominator. So that's how I ended up with a 4, right? I ended up with 4 and y in the denominator here. Okay, next we're going to solve each equation round to the nearest 10,000th place. That is 4 decimals. Okay, so our goal is to solve for x. So in order to solve for x, what I need to do is I need to isolate the e to the negative 2x. Okay, well, first thing I'm going to do, I'm going to subtract 4 from both sides. So that's going to be 3e to the negative 2x equals 6. Let's get rid of the 3, so we'll divide both sides by 3. So we have e to the negative 2x equals 2. Now I'm going to go back to one of these properties. Notice natural log of e to the x just ends up giving me my exponent. Okay, so natural log, so basically natural log of e to whatever will give me whatever is in the exponent. Okay. So what I'm going to do is I'm going to take the natural log of both sides. So whatever I do to the left side, I have to do to the right side. All right, now what? Well, the natural log of e basically cancels. I end up with negative 2x equals natural log of 2. And then I'm going to divide both sides by negative 2. So on my calculator, I'm going to take control. The natural log button is just above the e to the x. So we'll do control, then that e to the x button gives us natural log. 2, make sure you go outside the parentheses and divide that by negative 2. So we get x is negative 0.3466. Again, we're making sure to round to the nearest 10,000th. Okay, if you want to pause and try the next one on your own, otherwise I'll just keep going. Again, I want to try to isolate the e to the power first. So I'm going to add 12 to both sides. So that gives me 27, right? We'll divide by 3. So we'll get e to the 4x equals 9. Okay, same idea. What I'm going to do is I'm going to take the natural log of both sides because I want to get that 4x out of the exponent. So natural log of e cancels. We get 4x equals natural log of 9. Divide both sides by 4, and we get, let's take a look. So natural log, of 9, and we're going to divide that by 4, 0.5493. Okay, another solving. The last two had e to the x involved, or e to a power with x. Now we have a natural log. Okay, so first thing we want to do is let's divide both sides by 2. So I have natural log of 5x equals 3. Now remember, natural log is the same thing as a log with base e. So now what I can do is I can rewrite this, right? So remember there's a little base e. Let's change this to exponential form. So little base becomes a big base to the third power equals 5x. Again, what are we doing here? We're solving. We're solving for x. So if I divide both sides by 5, let's see what we get. So again, I'm going to find my, sorry about that. Let's see, e to the third power. Make sure to go out of the exponent. So I use my arrow, divide by 5. So we get 4.0171. Okay, let's keep going. So here I see a coefficient in front. Let's multiply both sides by 3. So I get natural log of x equals 6. Now let's rewrite it in exponential form. So remember there's an e there. E to the 6 equals x. So do e to the 6. And, I'm going to press my up arrow. I want to highlight it and press enter. I want to get a little bit more detail since I want 4 decimal places. So that's going to be 403.4288. Okay, so that's the first part. Now we're going to see what's one example of how we use e. So remember I had said that e is a really important number. Again, e is about 2.7. Okay, so a number between 2 and 3. But as I mentioned, it has lots of real applications in financial situations and also when we look into the sciences. So let's take a look at this formula. This formula here is for continuous compounded interest. Before, when we looked at compounded interest, we looked at quarterly was 4 times a year, monthly was 12. So this formula is actually easier because it's just compounded continuously. Now, we should recognize some of these numbers. A is the amount after a certain number of years. T is years. P is our principal amount, so that's what we're starting with. And R is the interest rate. Just make sure you always write that as a decimal. So we have A equals PE to the RT. So no longer do we have to worry about when we do compound interest, there's no 1 plus R over N, right? This one is actually an easier formula to use. Let's take a look. Okay, so we're going to deposit $700, paying 3% interest, compounded continuously. And we want to find out what is the balance in 8 years. Okay, well, let's see. 700 is the principal amount. 0.03 is the interest rate. Compounded continuously, as soon as I see that continuously, I know it's going to be an A equals PE to the RT. Some students will call it APERT for short. What is your balance? So that's asking for what A is when T is 8. Okay, so A equals PE to the RT. So we go to our principal amount, that was 700. Just stick that letter E in, okay, that's part of the formula. And then to the R, 0.03 times T power. Okay, so we can just all plug this right in to our calculator at once. So I'll do 700, click the E button and it'll automatically multiply, and it'll make that exponent. and we want 0.03 times 8. So this is a monetary unit. So what is your balance, right? So what's the balance after that amount of years? So we'll do 889.87 cents. So we'll just always round to that 100th place, right, for the nearest cent. Okay, how long will it take the balance in your account to reach at least $1,200? So now I'm giving you the end result. Okay, so remember, it was A equals PE to the RT. So I give you the end result, the principal amount. So we started with 700. E, the rate was 0.03, and T, right? How long will it take? So I'm trying to figure out how many years. Okay, so if you remember on the previous page when we were solving with e to a power, so first thing I want to do, let's go ahead and divide both sides by 700. Now I'm just going to leave that as 12 over 7. I'm not going to bother plugging into my calculator until I isolate the variable. Okay, so I have e to the 0.3t. Now remember, what did we do previously when we had e? So anytime we have e with an exponent that has a variable, we're going to go right to natural log. So I'm going to do natural log of 12/7 equals natural log of e to the 0.03t. So that gives us natural log of 12/7 equals 0.03t. Remember, we're trying to solve for t, so now the last step, I just need to divide the bottom, or divide natural log of 12/7 by 0.03. So let's take a look. So I have natural log of 12/7. Make sure you go outside of the parentheses, divide by 0.03. And it looks like about 18 years. So t is about 18 years. Okay. C, how much would have to be deposited in order to reach a balance of $1,500 after 12 years? Okay, so we want to end up with a balance of $1,500 when t equals 12. So going back to this formula, what are we trying to find? Well, how much would have to be deposited? That's the principal amount. So that's actually what I'm looking for in this case. So instead of assuming we're going to invest $700, we're going to say, okay, I want to end up with $1,500. I got to figure out what amount am I going to start with, and then it's going to be E. It's still 0.03, and I'm going to multiply that by 12, right, because that was T for years. Okay, so I have 1,500 equals PE to the 0.36, right, 0.03 times 12. Well, E to the 0.36, it's just a number. Remember, E is about 2.7. So I'm going to go right to dividing both sides by that number. And then I'm going to type that in. So I'm going to have 1,500 divided by E to the 0.36. And that's going to be 1,046 and 51 cents. That means I need to start with that amount. So I have 1,500 after 12 years. And that's it. And next lesson, we will do some more applications to these logarithms and E.